So let's say you have got an API working fine, serving everyone, and then one client, buggy code, or just hammering you on purpose, fires off a million requests in a minute, and your service just falls over. Not because any request was hard, just too many at once. So you need a bouncer, something that says you have had enough, come back in a bit. That's rate limiting. And it sounds almost too simple, right? Count the request, reject once they cross the limit. Like how hard can counting be? Turns out the counting itself is the easy part. What everyone quietly gets wrong is everything around it. So let's build one and watch it break. So the simplest thing you had reached so far, and honestly I have shipped exactly this, is a counter per window. Limit is, let's say, 10 requests every 10 seconds. So you keep one number per user, each request add one, cross 10, you reject. And every 10 seconds the window resets, counter back to 0. And it's clean, right? One number per user, dead cheap, nothing fancy to store. But watch what happens right at the boundary. Let's say someone sends 10 requests at the ninth second. All of them are allowed. Counter is at 10. Then at 10th second, the window resets to 0. And at 11th second, they send 10 more, also allowed. So that's 20 requests in about 2 seconds. But each window only ever counted to 10. On paper, nobody broke the rule. The limit said 10 per 10 seconds. They got nearly double in a 2-second spike. And your service absolutely feels that burst. That's the fixed window whole problem. The reset is a cliff. Line up on both sides of it and you punch right through. Okay, so the problem was that hard reset. So what if we don't reset at all? We just always look at the last 10 seconds, a window that slides along with you. No edge to exploit. The exact way is the sliding window log. You store a timestamp for every single request, and to check, you just count how many fall in the last 10 seconds. No boundary to game anymore because there is no boundary. But feel the cost, a timestamp for every request for every user. Figma measured this for 10,000 users, around 20 megabytes just for the log, and that's a small system. So the version basically everyone actually ships is the sliding window counter. It's an approximation, but a really cheap one. You keep just two numbers, how many requests in the current window and how many in the previous one, and you do a weighted guess. Let's say the limit is 50 a minute. You are 15 seconds into the current minute with 18 requests so far, and the previous minute had 42. So you would assume those 42 were spread out evenly, and you take only the part that still overlaps your window. That's 45 out of 60 seconds. So 42 times 3 quarters plus 18 comes to 49.5, just under 50 allowed. Two numbers instead of a timestamp per request. Figma's memory went from about 20 megabytes to 2.4, like 10 times less. The catch, and you should just say it out loud, it's an estimate. It assumes the previous window was smooth. If it was bursty, you are a little off. But in practice, that error is tiny, and almost everyone takes that trade. Cloudflare runs this at huge scale. And now, there is a completely different way to think about it, and it's the one a lot of the big APIs actually use. Forget Windows for a second. Picture a bucket of tokens. The bucket holds, say, 10 tokens and it starts full. Every request takes one token out, no token left, rejected, and the bucket refills at a steady rate, say, one token a second. So, on average, you are capped at one a second. But, and this is the nice part, if you have been quiet, the bucket fills back up. So, you can spend all 10 at once, a burst, and then you are throttled back down to the drip rate. So token bucket gives you a controlled burst plus a steady average, and it's cheap, one count, one timestamp. That's why Stripe uses it for their request rate limits. Now, if you have read about this, you have seen token bucket put head to head with leaky bucket. Like it's a fight, pick a side, and honestly, that framing is a bit wrong. Because there are actually two different things people call the leaky bucket, and they get mashed together. The first one, leaky bucket has a meter. Requests flow in, it leaks out a steady rate, and if it overflows, you reject. And if you look closely, that's just a token bucket in a mirror. One fills up, and you spend, the other fills up and you reject. Same exact decision. They are the same idea mirrored, not really rivals at all. The second one is genuinely different thing. Leaky bucket as a queue. Here you don't reject the extra requests. You hold them and release them at a constant even rate. So the output comes out perfectly smooth. No bursts ever leave. This is basically what Nginx does. It paces traffic. One caveat, since we care about being right, Nginx only queues like this if you configure a burst. By default, it just rejects. Small thing only, but it trips people up constantly. So the real question was never token or leaky. It is, do you let burst through or do you smooth them out? Reject or queue. That's the actual choice. There is one more worth knowing because the cleanest implementations use it. GCRA. Don't let the name scare you, it's actually a simple idea. Instead of storing a bucket and refilling it, you store a single number, basically the earliest time you are allowed to send next. They call it the theoretical arrival time. Every request just checks, are we past that time yet? If yes, allow it and push the time forward a notch. If no, reject. And you can even hand back exactly how long to wait. One number per user, that's it na. And you get a rolling window for free. Burn your whole limit in a burst and your capacity comes back gradually. Right away instead of waiting for some reset. Okay, so now we have got five of this fixed window, sliding window, token bucket, leaky bucket, GCRA, and the trap every other explanation falls into is to hand you that as a list to go and memorize. Don't memorize them because really you are only ever answering a few questions and the algorithm just falls out of your answers. First, do you want to allow bursts or smooth them out? That one splits the windows and buckets from the leaky queue. Then, when someone's over the limit, do you reject them or hold them in a queue? Then, do you need it exact or a cheap approximation is fine? That's a log versus counter. And the big one, does the limit have to hold across many servers or just one? Answer those and honestly the algorithm picks itself. And that last question, that's where this stops being about algorithms at all. So everything we just built quietly assumed one counter on one server, but you don't have one server. You have got a whole fleet of them. So now the real question, where does the counter live? If every server keeps its own, then 10 servers means a user can quietly do 10 times the limit. Useless. So the count has to be shared. Say one Redis that all of them talk to. And this is where it gets subtle. The natural way to write this is read the current count, check it, write the new count, read, decide, write. But picture two requests landing at the same exact moment. Both read count is 9 and both think great it is under 10 and allowed them. Both write 10. You have just let two requests through the last slot and cross a busy fleet. That little leak is happening constantly. That's a race condition. Now you will hear people say just use Redis INCR command. It's atomic, problem solved. And that's right for a plain counter. And wrong the moment your logic is anything more than that. Worth being precise about because this is the thing most explanations smear together. See, a single INCR is atomic. Redis runs them one at a time and hands each caller its own unique number. So if your whole check is just that one INCR, you genuinely don't have the race. Fair enough. The race shows up when it's read, then separately decide, then separately write, like a token bucket, reading the token count, and then writing it back. That gap is the leak. So the fix isn't use INCR command. The fix is make the whole read, decide, write happen as one atomic step. And the clean way is a tiny script, a Lua script that runs inside Redis, doing all the three steps on the server in one shot, with no gap for anyone to slip through. That's what Stripe and the good libraries actually do. One last real world thing, hitting a central Redis on every single request adds a network hop and your hot path for everyone. So, a common move Envoy does this. It's two layers, a rough local limit on each server to swat the obvious floods cheaply, and the precise global one sitting behind it. You trade a little accuracy for a lot less load. Okay, quick one that's close to home for me. Rate limiting AI APIs because they break the model we just built in a nice way. With a normal API, every request is roughly the same size. One request, one token from the bucket. But when you call an LLM, the cost isn't one request. it's the tokens. And one request might be 50 tokens or 50,000 tokens. So OpenAI, Anthropic, they don't just limit requests per minute, they limit tokens per minute, and not even one number. Separate limit for requests, for input tokens, for output tokens. You hit any of them, you are capped. And the genuinely hard part is this: with a normal request, you know its cost before you run it. With an LLM, you just don't. You don't know the full token count until it's done. So, how do you limit something whose cost you don't know yet? You reserve, then reconcile. For the input tokens, you estimate the cost upfront and hold that much back. Then settle to the real number as the request runs. And the output tokens, you just meter live as they come out. And under the hood, Anthropic literally uses a token bucket per limit, just continuously refilling. So it's the same idea we already built, just metering tokens instead of requests. Okay, flip it around. So far, you are the one doing the limiting, but honestly, most of the time, you are the one getting limited. You are the client. So, what do you do when something tells you to slow down? First, server tells you with a 429 too many requests and usually a retry after header. Literally, here is how long you have to wait, so wait that long. Don't just keep hammering. And when you do retry, you back off. Wait a little longer each time. 1 second, 2, 4, 8, exponential back off. Pretty standard. But this is the one that literally bites people. Let's say 1,000 clients all get rate limited at the same instant because the service hiccuped for a second. And all they do the same neat exponential back off. So they all wait exactly 1 second and all the retry at that same exact instant. And knock it over again. And all wait 2 seconds and all retry together. You have turned your own retries into synchronized stampede. It's a thundering herd. Same monster from the consistent hashing video, just wearing a different hat. And the fix is almost stupidly simple. Add randomness, jitter. Instead of wait exactly 2 seconds, it's wait somewhere between 0 and 2. Now the retries spread out instead of pulsing together. AWS has a whole write up on this. One line of randomness and the stampede is gone. So none of them is academic. Every one of these choices is running inside something you have used. Stripe, token bucket, Cloudflare, sliding window counter across millions of domains, GitHub, fixed window, and they just tell you your remaining budget right in the response headers. Nginx, Leaky bucket, the queue kind. Envoy, that's two-layer local plus global thing. And my favorite, Figma. They run the sliding window counter and they wrote up exactly why they rejected the token bucket. And the reason was that read then write wasn't atomic. The precise race we just talked about. That's not theory, that's a real team picking an algorithm to dodge a race condition. Same little handful of ideas, a different trade every time. And once you have got those four questions, you can look at any of these and basically reverse engineer why they chose what they chose. Okay, let's compress all of it. Rate limiting looks like a counting problem. Count the requests, reject the ones over the limit. But the counting itself was never the hard part. Fixed window, sliding window, token bucket, GCRA, they are all just answering the same few questions: bursts or smooth, reject or queue, exact or cheap. The actual hard part shows up the second there is more than one server, keeping that count honest atomically without quietly lying to yourself. So, if you take one thing from this, rate limiting isn't really a counting problem, it's a concurrency problem, wearing a counting problem's clothes. The algorithm, that's the easy part. Like I said at the start, it's everything around the counting that's the actual work. If this is the kind of thing you are into, and why underneath the what, subscribe. There is a lot more of this coming. I'll see you in the next one.